All right, even more fun with confidence intervals. Let's say that a logging company has hired us to estimate based on our sample of trees that's already in R. And our N is equal to the number of rows of our data here. So we have 31 trees and we have these variables. So let's look at volume. This is the quantity of lumber per tree in cubic feet. So let's say in our 31 trees, and we've sampled that from a population of capital N. Let's say we have 100 trees in the forest. We've sampled 31 of them and we got a mean volume per tree of 30 cubic feet of lumber per tree. And we want to know how many we'll have in our forest of 100 trees when we cut them all down for lumber. So here's the equation that we need to do that. Here's our sample mean multiplied by our uppercase N, or our population size. And that makes sense. If we have 30 cubic feet of lumber per tree and we have 100 trees, then we multiply those together and that will give us our estimate of the population total. So our estimated population total is equal to M times N, which is going to come out to be 3,017 cubic feet of lumber. But the logging company that's hired to do this wants us to be more precise. They want to give them an interval where we're 95% confident that our total population mean falls somewhere within that interval. So they've given us the confidence level of 0.95%. The equation that we're going to use is here. So here's our estimated population total. Here's our z-score from the t-distribution multiplied by the standard deviation of our sample divided by the square root of n. So this is the same thing as the confidence interval of the mean. And just like we did over here, we're going to multiply that by n to get the confidence interval of our population, or estimated population total. So here's how that will look. We're going to use the QT function, and remember we're going to go 1 plus our confidence level divided by 2, and our degrees of freedom are n minus 1. There we go. So if we go within 2 standard deviations of our mean, either 2 standard deviations below or 2 standard deviations above, that will occupy 95% of the area under the t-distribution curve with 30 degrees of freedom. We're going to multiply that by the standard deviation of volume and divide that by the square root of n. So that is this half of that equation, right? We're also going to multiply that by our capital N to turn that into our full confidence interval, okay? So here we have that full equation, right? N times Z, and Z is this whole area right here, right? So N times Z times the standard deviation of volume times the square root of N. So when we run that, our confidence interval is equal to 600 cubic feet of lumber. So if we take our population total minus our CI and our population total plus CI, so what we're saying here is that we are 95% confident that in our 100 trees, based on our sample of 31 of those trees, we are 95% confident that there is at least 2,400 cubic feet of lumber, but there's probably not more than 3,600 cubic feet of lumber. And that is how you calculate the confidence interval for a population total.